So what we have seen earlier is that Feynman loop integrals are typically divergent. And divergence comes from an integration region RC where all Euclidean loop momenta become large equally. So divergence comes from RC, which is given by all Euclidean loop momenta becoming large equally. So L bar i's are the loop momenta. Each Cartesian component of every one of them is taken to be k, and k goes to infinity. That is the region RC. And in position space, what this corresponds is all the interaction vertices approaching to a single point of coincidence. So that is how the position space interpretation is. Then we introduced superficial degree of divergence. That's given by omega equals L times D minus twice N. D is the dimension, L is the number of loops, and N is the number of internal lines. And using the graph identities, this could be brought down to the following form: D minus half D minus 2 times E minus delta N times V, where delta N is the mass dimension of coupling. And when this is greater than or equal to 0, the divergence, so the graph is superficially divergent, and when it is less than 0, the graph is superficially convergent. This expression is true for, okay, so let me write it here. For phi to the power n interaction in D dimension. Now, the question that we're going to ask now is, what is superficial about omega? Now, of course, if the graph is superficially divergent, then of course there is momentum divergence, because the power of momentum in the numerator is bigger than the power of momentum in the denominator, and there is no way you can avoid the divergence. So superficially divergent graphs are truly divergent. However, superficially convergent graphs are not always convergent. And we shall see, this is basically the point that is clarified in what is called Weinberg's theorem, which is what we are going to study now. So introduce subgraph. Given any Feynman graph gamma, subgraph is just any diagram that appears within gamma. So gamma 1 is a subgraph, is a diagram that appears within gamma. Now gamma 1 is viewed as a separate as a graph by itself, and then it will have external lines. Those external lines could be either external or internal to the bigger graph gamma. And complement of gamma must be another subgraph. Complement of gamma 1 is another subgraph. Let's look at an example. So here is an amputated diagram. It's of course in 5-4 theory, and then this is my gamma. This is a one particle irreducible diagram. Then you cut the diagram from here so that it gets separated into a diagram like this. This is gamma 1. And this is gamma 2. And when viewed as an individual graph gamma 1, these are external lines. And for gamma 2, these are external lines. So these external lines, these ones and these ones from gamma 1 and gamma 2 are actually internal to gamma, but these lines which are external to gamma 2 are also external to gamma. So lines that are external to the subgraph viewed as an individual graph can be either external or internal to the original graph. Now, generically, here is something that one can write down about the subgraphs. Suppose we have gamma 1 and gamma 2, which are connected by R propagators like this. And there are external lines. Some of them are connected to gamma 1, and some of them are connected to gamma 2. This can be a general structure of a graph, and this entire thing is gamma. Now, if r is equal to 1, then there is only one line here, and then gamma is not one particularly reducible, because if you cut this line, it will disintegrate into two parts. So r is greater than 1 when gamma is 1 bi. Now, the superficial degree of divergence for gamma, which is omega, can be written as the superficial degrees of divergence of the subgraphs omega 1 plus omega 2. These are the superficial degrees of divergence for gamma 1 and gamma 2 respectively. Plus, there will be a contribution from these lines. And the way is to find out the contribution to the superficial degree of divergence from this line is to figure out how many loops there are and how many propagators there are. Each loop will give you d number of momentum integral in the numerator, and each propagator will give you k square momentum square in the denominator. So let's take it to be 4 dimension. So d equals 4. So then if there are r lines, if you have 2 lines, then there is only one loop. Okay, there is only one loop momentum flowing here. So if there are r lines, there are r minus 1 loops. Each loop in 4 dimension will give 4 power of momenta in the numerator, and there are r propagators. Each propagator will give you 2 powers of momentum downstairs, so that is 2r. So these are r minus 1 loops, and these are r propagators.